Hello, class. Welcome back. So with the rest of this morning, we're going to be learning about the call stack. So this is kind of a generic programming concept. This exists in many programming languages, including both Python and JavaScript. I have chosen to demonstrate this in JavaScript this morning for no particular reason, but basically any programming language that has functions, it's going to have a call stack, which is any programming language. But so first, before we dive in, we should probably define some terms here. Can anyone tell me what is a call? I know I've been using this word a whole bunch.
If whenever you kind of tell like lines of code to run.
Yeah, a little more specifically though, not just any code.
When you're executing a function.
Yeah. So a call is when you execute, or sometimes you say invoke a function. Yeah. It's when you put the parentheses after a function. This is calling the function with these parentheses. Okay, so next question, what is a stack? I know you know this.
It's just a stack. It's like a list or an array. Yeah.
Yeah. It's a list.
Track of the function that you're in.
So just a plain stack is, it's like an array, like you're saying, but you can only add and remove elements from the top of it. Like a deck of cards or a stack of plates or something. So the first item that is added is the last one that is removed. So given that, what do we think a call stack is?
The order in which the functions get called.
Yeah, it's just a stack of calls. So every time you call a function, there's this like place in memory where the language has to keep track of all the functions that have been called, so it knows what it's in the middle of. And then when one function finishes executing, it knows where to return to. So I'm gonna code up a couple functions here real quick. They're gonna call each other. And so we can see this stack of calls. Oh, right, I'm not even. Autocomplete is just way too aggressive. So I've got my first function. It's going to tell us when it starts running, because that means it's being pushed onto the stack. And it's going to tell us when it finishes, that is when it is popped off the stack. But in the middle, it's going to call this other function second. So let's define that. And then inside of our second function, we will call yet a third function, which I need to define. So let's think about this for a minute before I actually just run the code. What order are we expecting to get all of these logs in? What is going to print out when I execute this?
I think it's just gonna go from the top to the bottom.
Just first function executing, first function resolving, second function executing. How do you mean? I mean, it does.
I think
go
I'm
from
just
top to
confused
bottom,
now.
but let's be more specific. Michael, did you have your hand up?
Yeah, so I think it will do push first function, push second function, push third function, hello world, pop third function, pop second function, pop first function.
Okay, sounds like a good guess. People have any other theories? Evan?
Yeah, so I could be wrong, but I don't see anywhere where you're like printing out like const first. So like it's just gonna, like in my mind, it's just gonna run and it's just gonna say great. It did all that, but it didn't print anything out. Is that right?
Yeah, so I actually forgot to call anything. Wait,
You have to use node.
what am I?
Evan wins.
Oh my gosh, why am I?
Nothing will print.
Okay, anyways. I know how to program. Okay, so you're right, I didn't actually call anything. So with no calls, there's no call stack. So let's actually call something. So we'll just call first, which calls second, which calls third. So I believe this was what you just said. So the first function gets called, and that's pushed onto our call stack. Then the second function gets called and it's pushed onto the call stack. And the third function, and then we get our hello world. The third function resolves. And then once the third function ends, we return back to our second function. And that ends, and then we return back to our first function, and then we are done. Now, if we want to visualize this a little differently, I'm going to actually use the debugger here. I'm going to set a breakpoint here before we actually call first. I'm going to run and debug. So now what I'm going to do is I'm going to use this button here, step into. This is going to let us proceed one line at a time. And if it encounters a function call, then it's going to go into that function and then go through the lines of that function one line at a time. So this is like a very slow way to see exactly what our program is doing. But you can note that there's this section on the bottom left that we haven't used before called call stack. You can guess what that's about to show us. So I'll go step into one. You can see on the call stack, this anonymous, that's kind of like our root base of the call stack. I don't know, it's the bottom of the stack, I guess. But we've put this first function on top of it. Wait, did I just press the wrong button?
I think you hit next because you're trying to step into a console log, right?
Maybe I need to practice the debugger a little bit more. Anyways, now we step into second. So now the second function has been executed. And we look at the call stack. So we've got our base at the bottom first, second is on top of it. We step forward, and then we step into this call to third. And so second hasn't finished executing, first hasn't finished executing, but now third is, we're in the middle of third, so that's on the top of the call stack. So we'll just step forward a little bit here. And so now the third function finished, you can see that that has been removed from the call stack. And now we're back in the second function at its last line. If I step forward, and then step forward again. So then the second function has finished executing. So we pop the second function off the call stack, and then we go down to the first function because we were in the middle of that, and then it goes to our console log here. Step forward. And then first has been popped off the stack because that finishes, and now our program is done. So I hope that little visualization there of the layers of the stack going on and off helps you kind of visualize what's going on. It's not outrageously complicated. It's just a list of all the functions that are currently unresolved, the things that we're in the middle of, and what has called what. Does anyone have any questions about this so far? No? Okay, so there's just one more thing that I want to show us here real quick. So what happens if we get an error while our code is running, but it's from some function inside of some other function, inside of some other function? This is when you're going to see the call stack more commonly. Evan, question?
No, I thought you were asking a question. Sorry.
I mean, do you have an answer?
Yeah. I think your question was like if we get like an error, so it'll stop at that point in the stack. So wherever you are, it'll stop right there, and anything below in the stack, it's not gonna even run.
Yep, for sure. Okay. So we got some of the console logs, as much as we could do before encountering this error, which is an unhandled error, so that causes the program to halt. But then our terminal here gives us a lot of interesting information. So, the first thing that I need when I'm debugging any code is the file name and the line number. So this is super helpful, telling me, which file went wrong through the error, what line it happened in. So that helps you kind of like jump right to where the issue was. But sometimes this file name and line number is going to be a little bit misleading because you called a function inside of some other function inside of some other function. And so the actual function that threw the error is not going to be interesting. So like for an example of that, let's say you have like just a really generic function in your application that calculates square roots. So this is just like a really generic function. So use it all over your application. It's not specific to one module or one part of it. Anywhere in your app where you need to calculate a square root, you're going to import this function and use it. However, your application can't handle square roots of negative numbers. We're not getting into complex numbers in this class. So let's say that this helper function, whenever it gets past a negative number, it just throws an error. However, if you're going to be using this function from various different parts of your code, then this line over here with the file name and the line number is not going to be very useful. It's just going to tell you that your square root calculator threw an error. But what you really need to know is who called my square root calculator that they were passing in a negative number, causing it to throw an error. So the answer to that question is in the call stack. So this next bit of information here below the file name with the line number, this is the call stack. This is the list of all the functions inside of functions that Python, or well, that JavaScript here was in the middle of at the time when the error occurred. So this happened in the third function on callstack.js line 19, which was ongoing in the middle of the second function, which is in callstack.js line 13. And of course, that was happening in the middle of first. on call stack JS line 7. And then it gets deeper into other things that I don't really know about.
Yeah, I don't know what all the module compile object. It's like, looks like it's, I don't know what that stuff is either, to be honest.
Yeah.
The stuff you ignore.
Yeah, it's the stuff you ignore. There's some base, some foundation of the call stack that Python is aware of that's beneath the code I'm actually writing. But like, honestly, I like to tell people, just as generic debugging advice, when you see big scary error messages like this, kind of the first thing that you might want to do is look at all these files and ask yourself, which ones of these did I write? Because, you know, these files here, I have no idea what these are. I didn't write them. I'm not responsible for them. So I'm not about to open them up, if I even can, and see what's going on inside them. But these files I did write. And so I'm going to always assume that the problems in my code are from mistakes that I made. It's not that JavaScript is messing up. It's I made a mistake in my code. So I'm going to look at the files that I wrote and see if I can find a problem somewhere in there. But yeah, so this is what the call stack is for. It's for debugging, to know where the error went wrong. In my opinion, this is like absolutely essential to have this information in order to debug anything, really. I've been in environments where that was not the case, and it was super frustrating, working with people who I felt like either were not great debuggers or just didn't know what was going on in general. But we had this like really sophisticated logging and analytics tool that we were like paying a whole bunch of money for every month. And it gives us tons of information about how our application was performing and what it was doing. But it gave us everything except for the call stack. And so, like, practically speaking, people were unable to debug common issues because our super fancy like logging and analytics software didn't give us the one piece of information that I really needed. But given that, if I do have this file name with a line number and a call stack, like that's probably all I need. And also an error message. Ideally, the error message is more descriptive than oops. It's something that you could Google and get some kind of unique information about. But yeah, this is like really critical information for debugging, getting that call stack.
Yeah, totally agreed, 100%. And it's a lot like, again, when I was in school, like doing and learning all this stuff, I'd be like kind of tracing through programs on paper or stepping through line by line and taking notes. And that's kind of what you do with the call stack debugging too. So it's like just that skill of like learning how to like walk through your program and have a mental model of what's going on at each step. Raphael, just out of curiosity, what kind of application, like what were you working on in that role where there was the like amazing logging monitoring tool?
Oh gosh, if I say that, then you'll know which colleagues I was complaining about. It was a financial technology application that helps people just like refinance their loans and whatever. I was a backend developer for a Node application. But it was like a microservices architecture. So like the backend that I was building didn't have its own front end, but it like communicated with a Ruby application, which did have its own front end. So that's why I was kind of talking about Ruby being a front end. Like it is really a backend language, but it was in front of our backend. So sometimes these terms front end and backend are relative to what is in front of you or in back of you.
Yeah.
Yeah, so sorry, with the microservices architecture, things get more complicated because it's like your whole application isn't just running on one server, but it's on multiple servers that have to communicate with each other. And so when an error happens, it's just hard to know like what you were really in the middle of, because it might have been one task that was happening across multiple servers.
There's an amazing YouTube comedy video for software engineers about microservices that I'm reminded of, and I'll just share it in the chat when class is over.
Oh wait, is that the what is it? The like birthday checker thing.
Yes.
Oh my gosh.
Yes, it is.
I actually love that video so much. I think that was published while I was working at this job with all the microservices. And I found it very very soothing, calming, satisfying, knowing that other people were so frustrated with microservices also, to the extent that they had to make a comedy sketch about it. And it very much like echoes all of my thoughts and feelings about working on microservices at that company. So I would definitely recommend that everybody watches this video because it's hilarious.
I'll share it. Yeah, it feels scarily accurate too. It feels like the people who made it must have like worked as software developers, because
Yeah.
they really kind of got it down.
Even the product manager in that sketch is like kind of scarily familiar to me.
Yeah, totally.
All right, so do we have any questions about the call stack before we continue onwards? No? Okay. So supposed to talk about recursion today a little bit. Honestly, I don't feel the need to get too super deep into it, given just how much it's already come up in this course. I feel like kind of already talked about recursion as much as I really care to. It's, you know, a trick that's useful for interviews, but it's not something that you're going to do practically all the time. Maybe just a couple of concepts that would be cool to mention just while we've got, you know, a few more minutes here. So let's say we've got a list. And we want to linearly search this list and find a particular letter we're looking for. So you should know how to do this. Just so we want to find the index of a particular letter. We can just iterate through the whole list. And then when we find the thing that matches, we return it. Great. So that's an iterative solution to this problem, just using a regular for loop. It's good to know, though, that any problem that has an iterative solution can also be solved recursively. I'm not recommending you do this, but just it's interesting to know philosophically that this is always a possibility.
Yeah, if anyone wants to, you can use recursion to traverse a linked list instead of a while loop.
Probably be passing the list in too. Target. So I guess this is a slightly different algorithm here. Instead of returning the index, since we're popping the item off, that's gonna destroy the array. So here we're just returning true if we are able to find the item, if it exists at all. So sorry, these are, I guess, slightly different solutions. Okay, here let's just turn true. Okay, there. So now these are actually solving the same problem. But here we are solving it recursively. So we just pop off the last item from the list. And if it's the one we were looking for, then great, we return true. The item exists in the list. If it does not exist, or if it's not that last item, then we just call the function again on our list. And that's going to, again, pop off the last item. And if it is the thing we're looking for, it returns true. But there's a problem here. So in our iterative solution, we just return false if we get through the whole list and don't find it. In our recursive solution, how do we know when to stop? How do we know that it doesn't exist in the list?
If the list is empty after popping all the last items, then it's not in the list.
Yeah, so what do you call that?
Like, what do you mean?
An empty array.
Base case.
Yeah, that's our base case. So that is the point at which you can no longer recur. Recursion is all about breaking a problem down into smaller subproblems. The base case is your smallest subproblem that cannot be broken down further. So in this case, the base case would be when the list is empty, you can no longer continue recurring. So we'll say if dot length is 0, return false. So this is our base case. We have to check this first just to make sure that it's actually valid to keep recurring. Because if the list length is 0, then we can't break this down to smaller problems. We can't find letter recursively anymore. So it's very important that your recursive algorithm is always able to stop itself somehow, that there is some mechanism that stops it from going infinitely. Definitely having a base case is the most common way to do that. I have found that there are some situations though where it's just really hard to know, like, when can you no longer continue? Like, it's maybe hard to define a base case. Maybe you just don't really understand the problem as well as you should, or it's just a very hard problem. But you do have some intuition that, like, it shouldn't take more than 10 or 20 or however many recursions. Like, if it takes more than 10 recursions to solve this problem, we're probably not solving the problem, but we're in an infinite loop. So in that case, there's a concept of max depth that can be kind of useful. So let's make a function here. So if So this is an approach that I've taken sometimes when, I've been called upon to write some recursive solution. It just seemed like the easiest way for me to think about some problem, but it was really unclear what the base case should be. And I didn't want to get into an infinite loop accidentally, because that is very bad, especially like in live production code. Might make your website inaccessible or crash or whatever. So this is kind of one strategy you can use to get around that. In addition to any other information my recursive function needs, I'm passing in how many times it has been called so far, and what is the maximum number of times I'm willing to call it. So I might call this like, let's see. So we start out 0 calls. And let's say max depth is 10. So we get, again, just printing out 10 times. Because yeah, I don't really have like a base case defined in terms of the problem itself, because there is no actual problem here. I'm not solving anything. It's just a function that's calling itself with no real logic. But if I'm just thinking, whatever problem I'm trying to solve, there's no reason why it should take more than 10 tries, 10 recursions to get this right. I could set a max depth just to make sure that this doesn't run away infinitely. And on that note, that's really all I have to tell you about recursion beyond what we've covered so far earlier in the course. I know it always comes up. It's kind of impossible to avoid talking about it earlier in the class. And so on that note, what questions have we got? Either about recursion, the call stack, really anything, data structures and algorithms. I know there's kind of a bunch of topics that we covered briefly today. Yeah, if there's anything people are curious about, previous in the week, later in the week, next week, this is the time for questions.
Was someone curious about the algorithmic complexity, like when you use recursion? I think that was in the chat.
Yeah.
I don't think it's always one thing. I think it's going to depend on the algorithm that uses,
Yeah.
it's being used.
So like in this case, find letter recursively, this is going to be O of n. It has the exact same complexity as the iterative solution. There's absolutely no way that this is going to take more operations than the length of the array. So yeah, it depends on the algorithm you're solving.
Yeah, and recursion gets used a lot. Like, I can't think of an algorithm off the top of my head, but like for kind of divide and conquer algorithms, like it's not just used for iterating through stuff. Someone was asking about that in the chat as well, and that was a good, or it came up, and that was a good point. Oh, Alicia, thank you for the reminder about breakout rooms and pair partners.
So do people have any more questions, or are we ready to get to lunch? We're 5 minutes over. Francisco?
Yeah, sorry about the background noise. Just real quick, can we expect tomorrow to go pretty much like last Friday?
No, actually. So that's a good question, but it doesn't have anything to do with today's lecture. So I'm going to stop the recording first.
Oh, thank you. Sorry about that.